Alright, so today is the remote day. It's the second day of analyzing the role of gravity in governing the solar system. There is no bell work today. Your first task is to complete the Google form on Google Classroom for solar system formation theories. This Google form is based on the notes from Friday. It has nebular hypothesis, stellar collision, fission theory, and capture theory questions on there, so feel free to use your notes on that. The second task for today is to watch this video and to take notes. Okay, you cannot watch this video until you have been to your in-class day because it is an additional, it's an extension of the information we learned in your class lab this week. So please don't watch the rest of this video until you've been to class and you're ready to take notes and answer the following problems. Okay, so from your lab on in-class day, there were two properties that we learned affects a planet's pull on you. So go ahead and get your lab notes out and figure out what those two properties are. Take a second, pause the video. All right, you should have learned that the two properties that affect a planet's pull on you are just its mass and its diameter, which actually can be put into an equation about gravitational pull or gravitational force. So here's the equation here, so go ahead and write that in your notebook, and we're going to take a bunch of notes under it and around it. So leave yourself some space. Okay, so you should have already written down this equation in your notes. Go ahead and keep taking notes on the rest of the stuff that I talk about today. Okay, so this is the gravitational force equation between two objects. Now, with our lab, we learned that one of those objects is often a planet, but it doesn't have to be, okay? So I'm going to make a little note here. I'm going to say one of these objects can be a planet, okay? So it's not very dark. I'll give it another marker. So in our lab, the two objects were the planet and then you being pulled by the planet, okay? So actually there's a force between both objects, between both the planet and yourself, and you're kind of pulling on each other. Obviously the planet's much bigger, so that affects how much it pulls on you, okay? But it doesn't have to be between a planet and a person, okay? So I'm going to write we're going to take this from our lab this week, two properties that affect pull, gravitational pull. And you guys already know this because I already talked about it. Mass, which we just talked about the planet mass, but actually a person's mass or the other object's mass also counts, is also important. And then diameter, which we're going to rephrase over here, okay? We're going to rephrase that as something else. We'll do it right now. We'll kind of rephrase it right now. It's similar to distance, like your distance from the center. If the diameter is bigger, you're farther from the center, okay? All right, so we're going to take some notes on this equation. F is force of gravity. So this is the actual calculation of the pull between two objects, the actual pull between the two. G is actually a gravitational constant. It never changes, okay? It's always going to be 6.67 times 10 to the negative 11th. That is the number it's always going to be. Okay, so if I ever asked you to calculate something, you would always plug that in for G. Okay, now I bet you could guess what capital M and lowercase m stand for. Okay, think about that. There's two objects pulling on each other, and what matters in pull, in gravitational pull that we haven't talked about yet, is mass. So M, capital M, is the mass of the larger object. This is often a planet, but it does not have to be a planet. Okay, remember, any two objects have a gravitational pull towards each other. That's actually, that's something that is a misconception. Planets aren't the only things that pull on you. Actually, any two objects near enough to each other have a pull on each other, which is kind of wild. Okay, the lowercase m is mass of smaller object. Okay, so that actually is really important as well. And the last thing we haven't talked about is r squared. And there's something that we haven't, there's the one other property that matters that we haven't actually touched on yet. So r is actually, stands for radius, okay? But think about radius. Think about a planet, here. Think about a planet, okay? And then think about you on the planet. Okay, here's you on the planet. Actually, I'll put you at the top because it's easier that way. And I know you're too big to scale on the planet, but here's the planet. Radius is from you to the middle. Radius is middle of the planet, okay? And if we're talking about radius, we can talk about radius for a planet, but for any other objects, if it's not circular like this, it's hard to use the word radius. So it might be easier to write distance between the centers of the two objects, okay? Between the centers of the two objects. Okay, so in the case of our lab, it was the center of the planet and the center of your body, okay? So it's really important that you get the distance between the two objects, but it's also between their centers, so that's really important to put as well in your answers, okay? So if we theoretically look at this equation, g times m divided by r squared, okay? So actually these things affect gravitational pull on you in different ways, okay? Let's look at the two masses. Okay, so we know that the two properties that affect a planet's or an object's force on another object, their pull between each other, is mass and distance, okay? But we're going to talk about how those actually affect the pull between the two, okay? So let's use our lowercase m and capital M, okay? Those are the masses of the two objects. Let's pretend those objects are the planet and yourself, okay? So the planet is going to be the capital M because it's the bigger mass, and lowercase m is the person, okay? So let's pretend that a person, let's keep the same person, is 100 kilograms. So I'm going to put 100 here, or 100 grams. No, kilograms, yeah, 100 kilograms, okay? And then that's their mass. And then let's put them on a planet that has a mass of 10 billion. I don't know, but that's probably still too small, I think, okay? 10 billion kilograms, okay? And then we're going to multiply g times capital M times lowercase m times the distance between the center, and we're going to get a certain force, okay? But let's move the person to a different planet that is, instead of 10 billion, let's put them on a planet that's 20 billion, okay? 20 billion kilograms, so twice as massive, twice as much mass. What's going to happen to the force? If we change this top number to double in size, what happens to the force between the planet and yourself? It's going to be a bigger force, okay? So it's going to also double in size. So what you're going to get is a direct relationship between mass and force. If you increase mass, force is going to increase in the same amount. So we're going to write that in a sentence over here. It's important information, but let me go look up how I wrote it. So as either mass gets bigger, or let's do increases. Let's use our vocab, our science vocab. As mass of either object increases, okay, sorry about the lighting. If mass increases, so does that gravitational force. So gravitational force of gravity So those are directly related. I'm going to turn off the lights so you guys can see that better. All right, now let's talk about the distance on the bottom, okay? Let's erase this information about the mass. Let's pretend the mass will stay the same. We're going to talk about distance. So distance from the center. Think about this picture over here. Here's the center of the planet, and here's you, okay? So think about distance. Let's talk about a planet that has a distance from its center, so it's going to be very small. Let's say the distance from the center is 1 million kilometers. Okay, that's your distance from its center. So we're going to pretend it's just a certain planet with 1 million kilometers from the center. Now, that's going to be on the bottom of a fraction. Okay, so what if we move you to a different planet that you are farther from the center? So the planet is bigger. Okay, so it would be a bigger planet. Okay, and you'd be farther from the center there. And that one is going to be 2 million kilometers from the center. Okay, so you've got a bigger number in the bottom of a fraction. Okay, anything divided by it, if the number gets bigger in the bottom, your overall answer gets smaller. Okay, so if the number on the bottom gets bigger, your overall answer gets smaller. That makes sense because think about if you are farther from a planet, if you're farther from an object, it's not going to be able to pull on you as much. Okay, so if you are farther away, the force decreases. Okay, we're going to write that out. As distance, remember from center, increases. So as it gets bigger, as you get farther from the middle, the force of gravity between the two objects decreases. It goes down because it can't pull on you as hard because you're farther away. Okay, so that is an inverse relationship. Those are inversely related. They are opposite of each other. The farther away you get, the less you can be pulled on. That's an inverse relationship. Okay, so let's look at some example problems to work on this. All right, so let's try some example problems. We have the equation here, and you have your notes from earlier. Okay, the first example is if I, the smaller object, so I'm this little m over here, move from Earth, which is the capital M, the larger object, to a newly discovered planet, which is the new larger object, and the only difference between the two planets is that the new planet weighs more, which planet will I weigh more on? Which planet will have a greater gravitational force between me and the planet? Okay, think about that for a second. Pause the video, try it on your own. Okay, so the answer here is, well, if all I'm changing is this capital M, so the mass of the bigger object, and the mass of the bigger object gets bigger, then the force is going to be bigger. So I want, which planet will I weigh more on? Which planet will have a bigger force here? It'll be the planet with the bigger M here. So I'm going to say the new planet weighs more. Okay, so I'm going to write in a full sentence, I will weigh more on the new planet because if the mass of the bigger object increases, so does the gravitational force that it has on me, the smaller object. Well, the more gravitational force it has on me is smaller object. Yep. Okay. So that's the answer there. But you have to use your notes and your reasoning from class. Okay. There's a why to it as well. Okay. Let's look at the next problem. If I, the smaller object, okay, I'm again this small m, move from Earth, the larger object, to a newly discovered planet, this larger object, and the only difference between the two planets is that the new planet is wider than Earth, which planet will I weigh more on? Okay, which planet will have a greater gravitational force between me and the planet? Okay, so take a second, pause the video, try to answer this one yourself. Okay, for this one, we are looking at distance between you and the center of the planet. So we are actually looking at the r at the bottom of the fraction, okay? So remember, if r gets bigger, the force gets smaller. The force on you gets smaller. So let's see which planet will I weigh more on. So I'm looking for a greater force here. So I'm looking for the smallest distance here, the smallest diameter, okay? So I'm looking for the planet that's less wide. So let's go reread the question. The only difference between the two planets is that the new planet is wider. Okay, so that means Earth is less wide, and so that means Earth's number down here is smaller, which means that the force it has on me is going to be bigger, which answers the question, which planet will I weigh more on? So I'm going to say I will weigh more on Earth because, oh yeah, there is a y part to this, you have to answer it. And you need to be writing these questions out in your notebook and the answers. Okay, I will weigh more on Earth because with when the width or diameter decreases, the gravitational force on me, the other object, increases. Okay, gets bigger. Okay, so that's the answer to that one. All right, make sure you're writing all these examples out in your notebook, and you're also going to have to write out homework problem number 1 and homework problem number 2 in your notebook, and then answer them as well in full sentences. Okay, so let's go ahead and look at those. Homework problem number 1. Your friend decides to be a part of the first community to move to a new planet. The new planet is exactly the same as Earth in every way, except that its mass is half the amount of Earth's. Okay, so its mass is half as big as Earth's. Which planet will your friend weigh more on? Which one will have a greater gravitational force between the object and the person, and why? Okay, so you've got to answer that question. And then the other one has 2 parts. Your friend decides to be a part of the first community to move to a new planet. So it's the same setup. The new planet is exactly the same as Earth's in every way, except that its diameter is half. Okay, so this is a little bit different. Its diameter is half the amount of Earth's. Okay, so on which planet is your friend closer to the center? Okay, so think about the problem here and decide which planet your friend is closer to the center. And which planet will your friend weigh more on, have more gravitational force, and why? So go ahead and answer those 2 problems and show your work in your notebook and upload all of this to Google Classroom.